Welcome to my new calculus channel. I am John Gabriel. In this YouTube I will be discussing one of Newton's publications called The Method of Fluxions in Infinite Series. And I'll be looking at what he described as reduction by division. Right? That's what you see at the top here. Reduction by division. Okay, what Newton's done here is very obfuscated, and it doesn't need to be that way. Most of you will not understand what he's done because you're just not smart enough, so I'm going to simplify this for you and show you that you can get this quotient that he gets down here in a much simpler way. Now, I think reduction by division is actually a misnomer because you're not really reducing anything, you're making it more complicated. I would rather call this division using partial divisors. And that's what I want to show you now in this particular example. I'm going to show you how to find that answer. In other words, a squared over b plus x, okay, using partial divisors. That's a term I coined, divisors, okay. And of course, if you have watched my videos on Newton and his fake infinite series, you will have come across this already, and also why 1/3 is not equal to 0.333 ... So you will have seen some of the theory behind partial divisors there. Let me do a simple little example first, and then I'll show you how to actually express this in one of innumerably many forms. Okay, in other words, there's no end to the number of ways that you can actually express this when you use the division method with partial divisors. Now, typically in long division, what you do is you have the dividend like that, okay, and the divisor. So it's just one whole divisor. But in fact, what you can do is you can have any linear combination of the divisor and any linear combination of the dividend. So for example, you could write this as 1 plus 2 plus 3 divided by any linear combination of 30, 10 plus 10 plus 10, or 15 plus 15, or 20 plus 10, or whatever else you wish. And you can do the division process using any one of these partial divisors, 1, 2, or 3. Or you could, and you can also change the partial divisors as you go along. For example, if at a certain stage you want to switch from this linear combination, you can go to a combination such as 4 plus 2, or just back to 6, or 2 plus 2 plus 2. It really doesn't matter. And the same thing with the dividend. Okay, so any combination here will do. 1 plus 29, 7 plus 23. It doesn't matter. The sum of the partial quotients up here will always give you the correct quotient, which in this case here is 5. Okay, so let's see how to do that very quickly using numbers. And if we say, let's divide 6, let's choose any two numbers. Let's say 4 plus 2 is 6, and then let's go with 20 plus 10, which is 30, right? Okay, and we can say if we say 4 goes into 20 5 times, then we've got 5 times 4 is 20 plus 5 times 2 is 10, and we're done, right? Okay, but let's not choose that. Let's choose something else. Let's choose 2 as a partial divisor and do the following. So let's choose 2 and say 2 goes into 20 10 times, right? And 10 times 4 is 40, and 10 times 2 is 20. And if we subtract these here, we're going to get minus 30, aren't we? Yeah? And of course we could rewrite minus 30 as, let's say, minus 10 or minus 6 and minus 24. We can choose anything we like. It doesn't really matter. Let's do minus 6 and minus 24, right? So minus 6 and minus 24. And now we can just switch over to 4 as a partial divisor. Okay, and we can just say 4 goes into minus 24. We don't even have to bother about the minus 6, and it goes into there how many times? Minus 6 times. Is that correct? Yes. So that will give us minus 24 minus 12, right? These two will cancel out, and minus 6 plus 12 is what? 6, yes? Okay. And so we could just come back here and say 2 goes into 6. We could, of course, split this up into linear combinations again, but I don't feel like doing it, so I'll just say 2 goes into 6 plus 3 times, yes? And then we'll have 3 times 4 is 12, and 3 times 2 is 6, right? And so what we have here then is minus 12, okay? And we can say, well, let's just choose the partial divisor to be 6 again, like that. And we can just say 6 goes into minus 12 minus 2, and that will give us minus 12, and we're done, okay? So, and this here should be 5. 10 minus 6 is 4, plus 3 is 7, minus 2 is 5. So it doesn't really matter how you do it. Incidentally, you could have chosen any number you liked as the first divisor up here. It doesn't really matter. And let's just do one more example to show you that neither of these partial divisors has to go into any of the partial dividends exactly. Watch. I'll give you a little example here, okay? So, for example, let's get rid of this. Let's even just, for good measure, just start off with let's even just change this. Let's make it 1 plus 2 plus 3. Doesn't really matter. We could leave it as 4 plus 2, but I just want to show you that you can choose any linear combination. And let's just say that 1 goes into 20, let's say 7 times, okay? It doesn't really matter because this process will work regardless. So that will give us 7 plus 14 plus 21. Yes? Okay. So now if we look at this here, 20 minus 7 is what? 13, yes? Okay. And 10 minus 14 is minus 4 and minus 21. So ultimately what we have here is 13 minus 25, right? 13 minus 25. And what is 13 minus 25? It's minus 12, right? So let's just rewrite that as minus 12. Minus 12, or... and it doesn't matter how we write. We can write it as minus 12, but then we'll finish quickly, and I don't really want to finish quickly. If I write minus 12 here, then I can just turn that divisor back into 6 and say it goes into minus 12, minus 2, and I'm done. It's 5, right? So I'm going to change it a little bit just for the heck of it and say, let's make it minus 8 minus 4, right? Minus, or let's make it minus 2 minus 4 minus 6. How about that? So let's make, that's minus 12, isn't it? Yes. So let's make it that. Then we can choose any one of these divisors. If I choose 1 here, I can say 1 goes into minus 2 times, and as you can see, then I'll get minus 2, minus 4, and minus 6, and we're done, and that's 5, right? Okay. If I choose 2 instead of 1 as a partial divisor, so I'll say, okay, let's say 2. I could say 2 goes into minus 4. 2 goes into minus 4 minus 2 times, and then still again the same result, right? And 3 goes into minus 6 minus 2 times. But I don't even have to do it that way. I could, for example, say here, let's see, I could say 1 goes into minus 4 times, right? No problem. Then I'll have minus 4 times 2 is minus 8 and minus 12, right? So if I subtract all these, I can see that these are going to disappear, and I'm going to say minus 2 minus minus 12 is 10, and minus 6 minus minus 8 is plus 2, right? So what I've got down here is 12, right? And I could just change this divisor here to let's say 5 plus 1, just for the heck of it. And then I could say 5 goes into 10 twice, right? So that would be plus 2, and that will be 2 times 5 is 10, right? And 2 times 1 is 2, and we're done. And 7 minus 4 is 3, plus 2 is 5, and the result is once again the same. So really, what you're doing here is you're measuring the dividend with the divisor, but you're not, in this case, measuring it with the whole divisor, but with parts of the divisor. And so you ask, why do you get the right answer all the time? Well, when you put a partial quotient up here, whatever that partial quotient is, it doesn't matter. It could even be a fraction. I could have, for example, started off with 3/4 there. It doesn't matter, because I'm going to multiply every one of these partial divisors by the partial quotient, and the answer will readjust so that no matter what I do, I'm going to ultimately end up getting the right answer. Does that make sense? Okay, you may want to just look at these other 2 videos, and also another video, a very important video called Division, What is Division, and Polynomial Division, It's also one of the YouTube videos available on my channel, and this explains this process again in more detail in the process of partial divisors. Alright, so now let's get rid of that and that also, and I'm going to show you now. In fact, I could have just said new, make matters simpler. I'm going to show you now how to divide a squared by b plus x. Okay, so using this method of partial divisors, here's what I have: a squared divided by b plus x. It doesn't matter which of these I choose to divide into to measure a squared with. Well, let's just choose b first. If I choose b first, I'm going to get a squared. That's horrible. Let's write it out properly. I'm going to get a squared over b, right? Now multiply it by both terms. So here I'm going to have a squared plus a squared x over b. And I'll do the subtraction, and I'll have minus a squared x over b, right? And again, I don't have to choose to divide by b here. I could choose x, but I'm going to choose b, because if I choose x, I'll end up just going back to what I had. So I'll choose b once again, and what I'm going to get here is a squared x over b squared, right? So I multiply that by b, and I'll have minus a squared x over b minus a squared x over b squared, which leaves me with a squared x over b squared, and I can see that the next term there is going to be a squared. Did I make a mistake there? That's x squared, isn't it? Yeah, I'm sorry, that's x squared there. And the next term is going to be ax squared over b cubed, right? And you can see that a certain pattern here is emerging, so that the next one will be a cubed x cubed over b4 plus dot dot dot. And of course that particular series is what you have down here. Okay, is what you have down here. Let me just move this up here a bit so you can see. So if you go over here, you'll see that that's a, which is a squared over b minus a squared x over b squared plus a squared x squared over b cubed, etc. So you end up getting the quotient like that, but it's not really the complete quotient, and that's what I'm going to be talking to you about. It's actually not the complete quotient. So at any one of these stages here, we could have chosen to stop this process to get an exact value, okay? So, for example, if we stopped here, then we would have that a squared plus bx is equal to what we've got up top here. Let's just copy that. I don't feel like writing it out again. Like that. Copy this, put it down here. It's going to be that plus this last term, which is a squared x squared b squared over b plus x, right? Okay, so this here is exact. There's no infinite series here. And of course you can see that if we carried on, you'd have an extra term here, and the next one if we continued on to this next step here with this partial division process. Now Newton has a Blond moment. A Blond moment. And watch what he says. He has a Blond moment. And he says over here, the quotient therefore is this, which series being infinitely continued, well, there's no such thing as infinitely continued, that's just garbage, will be equivalent to a squared over b plus x. Did you get that? Will be equivalent to a squared over b plus x. That is false, okay? That is wrong. That is not true. It's never equivalent, right? So you cannot just say what Newton said by adding dot 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 at the end, that this here is equivalent to a squared over b plus x. Equivalent means equal. It is not equal. It's approximately equal, okay? It's a big difference. And that is why you can say stupid things like 1/3 is equal to 0.333 dot dot dot, okay? This nonsense began with Newton. He had a Blond moment, and guess what? Euler picked up on that Blond moment in his Elements of Algebra, and then the rest of you morons continued with the Blond moment. Yeah, that's right. The majority of you morons who think that this here is true, it's not true. It's false, okay? It's false. I have much more to say about this, but I'm feeling a little tired now and a little unmotivated, so I think I'll stop. But I hope that you'll join me next time when I have some more inspiration. I've enjoyed chatting with you. This is the New Calculus channel. I'm John Gabriel. Goodbye.